Welcome to the Deep Dive, your express lane to understanding groundbreaking research. Today, we're plunging into a challenge as fundamental as large language models themselves, their insatiable appetite for computational power and memory. Imagine a world where LLMs are just as powerful, but, a fraction of the cost. Where the future of AI isn't solely tied to throwing more hardware at the problem, but to smarter, more adaptive designs. That's the fascinating promise of Mixture-of-Recursions, or more. This deep dive is designed to be your shortcut to truly understanding this, significant advance in efficient large model design. We'll unpack the core paper, Mixture of Recursions, learning dynamic recursive depths for adaptive token-level computation, extracting the most crucial concepts, methodologies, and empirical results. It's about teaching LLMs to think smarter, not harder, intelligently allocating computation. This could really redefine how we approach model design.
Indeed. The core problem, as you alluded to, is the immense scale. While large transformer models are undeniably powerful, their memory footprint and computational requirements measured in floating point operations make both training and deployment incredibly expensive.
Especially outside hyperscale data centers,
Right.
right?
Exactly. Especially then.
So it sounds like previous efficiency efforts were maybe tackling symptoms, but not the root cause in a unified way.
Precisely. Existing efficiency efforts have largely targeted one of two axes, either parameter efficiency, think reducing or sharing model weights, a technique often called layer tying, or adaptive computation, which is about spending more compute only when truly needed, much like early exiting, where a token finishes processing and leaves the network early. What's fascinating here is that a unified architecture effectively combining both has been, missing. Recursive transformers, which reuse shared layers, offered a strong foundation for weight sharing. But prior attempts at dynamic recursion faced practical hurdles, like specialized training or deployment challenges. They often just defaulted to fixed depths.
Meaning they weren't truly adaptive at the token level. Same compute for every token.
Right. Applying the same amount of computation to every single token, regardless of its individual complexity. Not very efficient.
So Moore emerges as this unified framework fully leveraging recursive transformers. Its core idea is quite clever. It trains lightweight routers end-to-end to assign token-specific recursion depths. This allows the model to dynamically decide how many times a shared parameter block is applied to each token based on its specific thinking depth needed, like a conductor.
That's an excellent analogy.
Yeah.
Huh? And this dynamic token-level recursion naturally facilitates what the paper calls recursion-wise key value, or KV, caching.
The KV cache. That's the memory component for attention, isn't it? It's exactly. With Moore, it means selectively storing and retrieving KV pairs only for tokens at their assigned recursion depth. This significantly reduces memory traffic and improves throughput. So if we connect this to the bigger picture, Moore inherently combines three powerful efficiency paradigms within a single architecture. It ties weights for parameter reduction.
Got it.
It routes tokens to cut redundant FLOPs.
Mm-hmm.
And it caches key values recursion-wise to reduce memory traffic, all in one. The key contributions highlighted in the paper are really substantial. First, Moore is presented as this unified framework, bringing together parameter sharing, token-level adaptive thinking depth, and memory-efficient KV caching.
All in one pack.
All in one package. Second, it introduces dynamic recursion routing, a router trained from scratch to assign per token recursion depths. This is crucial because it aligns training with inference behavior, It eliminates those costly post hoc stages that often complicate adaptive models.
Okay, that makes sense. Aligning training and inference is always a challenge. Definitely. Third, through extensive empirical validation across models from 135 million up to 1.7 billion parameters, Moore consistently forms a new Pareto frontier. So at equal training FLOPs and smaller model sizes, it significantly lowers validation perplexity and improves few-shot accuracy.
That's impressive. Better results with fewer parameters.
And finally, its efficient architecture dramatically reduces training FLOPs by selectively engaging only essential sequences in attention. Plus, it significantly enhances inference throughput via reduced KV cache sizes and this novel approach to batching.
Fascinating. Okay, now let's peel back the layers. Let's understand how Moore actually achieves all this. What's under the hood?
Right. It all starts with building on an existing clever idea. Recursive transformers.
Yeah.
Think of them as the foundational scaffolding for this new architecture.
Okay.
In a standard transformer, token representations are built through a stack of unique layers, right? Recursive transformers, by contrast, aim to reduce parameter count by reusing shared parameter blocks, often denoted as phi prime, across multiple recursion steps. This design allows for more computation, increasing the effective network depth without actually increasing the total parameter size.
More compute bang for your parameter buck, essentially.
Exactly. And the paper explored 4 distinct parameter sharing strategies. There's the cycle strategy. Instead of all unique layers, Moore reuses a set of core layers repeatedly.
Like looping through them?
Yeah, imagine having a few master layers that tokens cycle through multiple times, building up their representation. This encourages deeper iterative refinement, but maybe limits capacity for diverse features sometimes.
Okay.
Then there's sequence sharing. This reuses the same layer consecutively multiple times before moving on. Can sometimes lead to redundant features, potentially.
I see.
The middle cycle and middle sequence variants are designed to strike a balance. They preserve unique parameters at the very first and last layers, but share weights only among the intermediate layers, trying to get the best of both worlds.
Makes sense. Keep the start and end unique, share the middle.
Precisely. And these recursive models offer 2 key efficiency benefits. First, obviously parameter reduction. They reduce unique trainable parameters by a factor equal to the number of recursions. Amortizes the memory footprint. This is particularly efficient for distributed training setups, like using fully sharded data parallel, FSDP, which helps manage huge models across many GPUs. Second, and this is quite innovative, they enable a novel inference paradigm, continuous depthwise batching.
Continuous depthwise batching. What's that?
It's a technique that allows tokens at different stages of recursion to be grouped into a single batch, all utilizing the same shared parameter block. This eliminates idle periods on the GPU, those bubbles, and leads to significant throughput gains during inference.
Ah, so keeping the hardware busier more consistently.
Exactly. Much better utilization.
So if recursive transformers were already a step in the right direction, what were their biggest limitations that Moore specifically set out to address?
Excellent point. Prior recursive works typically applied a fixed recursion depth to all tokens. Ignored their varying complexity was a one-size-fits-all approach.
Inefficient.
Very. Also, they often used distinct KV caches for each depth, which meant they weren't really reducing cache sizes effectively and could lead to high retrieval latency during inference. While post hoc adaptive methods existed, they often required separate, sometimes performance-degrading training phases or introduced complex engineering challenges. Moore is designed to overcome these by learning the optimal recursion depth dynamically during pre-training.
Okay, so that's where Moore's real genius shines, isn't it? And its 2 main components: how it intelligently routes tokens and how it handles those KV caches. Let's break down the routing first.
That's precisely where the breakthroughs lie. For routing, Moore explores 2 main strategies: expert choice and token choice.
Expert choice.
Yeah.
Like mixture of experts.
Sort of inspired by it, and also mixture of depths. Each recursion depth essentially acts as an expert. It decides which tokens get to go deeper into the model based on their internal readiness score, you could say. This approach ensures efficient load balancing, because a static number, a top KL of tokens, can be selected at each step.
Okay, that sounds good for managing compute. Any downsides?
Well, it did pose a challenge.
Yeah.
A potential for information leakage during training. The model could inadvertently see future steps, violating causality.
Right. That's a problem.
Yeah, but the paper tackles this head-on with clever mitigation strategies. Things like using an auxiliary router or an auxiliary loss function.
Okay. And the other one, token choice.
Right. In contrast, token choice routing commits each token to a full sequence of recursion blocks right from the start via a single routing decision.
So one decision up front determines the whole path.
Exactly. This approach is inherently free from that information leakage issue.
But I bet load balancing is harder.
That's the limitation, yeah. Inherent load balancing challenges. Tokens might be unevenly distributed across the experts or recursion depths. To address this, they use techniques like a balancing loss, which encourages a more uniform distribution, or loss-free algorithms using router biasing. Critically, the paper calibrates these strategies carefully to ensure a fair comparison, aligning their token allocation budgets for equal compute.
Got it. So 2 main ways to route, each with trade-offs and mitigations. And what about the KV caching? How does Moore manage that crucial memory component dynamically?
Right. Dynamic depth models often struggle with KV cache consistency and size. Moore addresses this with 2 powerful approaches: recursion-wise KV caching and recursive KV sharing.
Okay, recursion-wise caching.
With recursion-wise caching, only tokens routed to a given recursion step actually store their KV entries at that specific level. Attention is then naturally restricted just to those locally cached tokens.
So it keeps things local.
Exactly. It promotes block local computation, significantly improving memory efficiency and reducing I/O demands. It cuts KV memory and I/O by approximately half in a common setup and drastically reduces attention FLOPs.
Sounds very efficient. And the other one, recursive KV sharing.
Recursive KV sharing leverages the fact that all tokens go through at least the first recursion block. So it caches KV pairs only at this initial step and then reuses them across all subsequent recursions.
Ah, so you only cache once.
Essentially, yes, for the shared steps. While the query length might shorten as tokens exit, the key and value links maintain the full sequence from that first step. This offers maximal memory savings by skipping KV projection and prefill operations at shared depths. KV memory gets reduced significantly.
But what's the catch?
Well, attention FLOPs only decrease proportionally to the token ratio, which is less reduction than recursion-wise. And high KV I/O can still potentially be a decoding bottleneck.
So clear trade-offs again, memory versus I/O versus FLOPs, depending on the strategy.
Exactly. You choose based on your specific constraints and goals.
This is where it gets really interesting. Theory is one thing, but what happened when they put more to the ultimate test in extensive experiments? What did the results show?
The main results are truly eye-opening. Under an equal training budget, 16.5 quintillion FLOPs, a huge number.
Wow.
The Moore model, specifically using expert choice routing and 2 recursions, achieved lower validation loss and actually surpassed the vanilla baseline in average few-shot accuracy.
Wait, better accuracy with fewer parameters? How?
It's remarkable, right? Moore did this despite using nearly 50% fewer unique parameters. The reason is Moore's inherently higher computational efficiency. It allowed it to process more training tokens within the same FLOP's budget.
Ah, so it learned more effectively from the data it saw within the same compute constraints.
Precisely. And even as the number of recursions increased to 3 or 4, Moore maintained competitive accuracy. It consistently outperformed the recursive baselines and stayed very close to the full capacity vanilla model. Then, when they compared performance under a fixed number of training tokens, 20 billion tokens, Moore again outperformed both vanilla and recursive baselines. Lower loss, higher accuracy.
And presumably used less compute to process those 20 billion tokens.
Exactly. It used 25% fewer training FLOPs. And that translated into significant practical gains. 19% less training time and 25% lower peak memory usage.
Those are serious savings.
Huge savings. And these improvements are attributed directly to Moore's hierarchical filtering and that recursion-wise attention mechanism we talked about. The choice of routing and caching also mattered, as expected. Token choice routing yielded lower performance compared to expert choice, which really underscores the importance of that fine-grained adaptive routing. And while KV cache sharing slightly reduced performance compared to independent caching, it did provide improved memory efficiency. That's a favorable trade-off for memory-constrained deployments where throughput is maybe more critical than peak accuracy.
So the bottom line is Moore shows we can move beyond just brute force scaling.
I think so. Moore really suggests a future where model quality isn't solely tied to astronomical parameter counts, but to smarter adaptive architectures. It could open doors for more accessible and efficient AI development.
That's a profound implication. Okay, and what about scalability? How did Moore perform when scaled up under different compute budgets? Did it hold up?
It held up very well. The isoflop analysis, which looks at scalability across different model sizes and compute budgets, proved Moore to be a highly scalable and parameter-efficient architecture. They tested Moore, expert choice, recursion-wise caching, and R3, against vanilla and recursive transformers from 135 million up to 1.7 billion parameters under various FLOPs budgets.
Right.
Remember, the Moore models had about 1/3 the unique parameters of vanilla. The key finding, Moore consistently outperformed the recursive baselines across the board. Now, while it slightly underperformed the vanilla model at the very smallest scale, 135 million likely due to a recursive capacity bottleneck there.
Okay.
That gap rapidly closed at larger scales. For models bigger than 360 million parameters, Moore matched or even exceeded the vanilla transformer, especially under low and mid-range compute budgets.
So it scales really well, particularly efficiently at larger sizes.
Exactly. These results strongly indicate Moore is a scalable and parameter-efficient alternative to standard transformers, achieving strong validation performance with significantly fewer parameters.
And for deployment, what about inference throughput? That's often a major bottleneck in real-world applications, isn't it?
Indeed it is, and Moore demonstrated substantial gains there too. It leverages that continuous depth-wise batching we discussed earlier.
Right, filling the gaps to keep the GPU busy.
Precisely. It maintains high GPU utilization by immediately replacing completed sequences with incoming tokens as others exit early. The results: All Moore variants significantly outperformed the vanilla baseline, even when vanilla was also using continuous sequence-wise batching.
Really? Even compared to optimized vanilla?
Yes. And increasing the recursion depth in Moore, say to 4 recursions, led to up to a 2.06x speedup with maximum batching.
Over double the speed.
It clearly shows that integrating depth-wise batching with early exiting significantly accelerates Moore's deployment throughput, makes it far more practical for real-time applications.
Let's get into some of the finer details now. The ablation studies often reveal the nuances of these design choices. What did they learn about the best way to do parameter sharing, for instance?
Absolutely. The ablations are revealing. When it came to parameter sharing strategies, the middle cycle approach consistently came out on top.
Middle cycle. That was unique first-last layers, shared middle ones cycling.
That's the one. It consistently achieved the lowest validation loss and highest accuracy across various model scales and recursion depths. Its superiority was especially clear at higher recursion depths, and during uptraining, from existing checkpoints basically, continued pre-training.
So the paper basically recommends middle cycle as the go-to.
Pretty much. It's presented as the consistently safest and most robust choice for both Moore and standard recursive transformers. The intuition seems to be that having dedicated first and last layers while sharing the intermediate ones cyclically gives you both good initial processing and final refinement, while still getting efficiency gains in the middle.
That's a strong recommendation. Okay, and what about the nuances of the routing strategies themselves? How did different implementations perform within expert choice or token choice?
Good question. For expert choice routing, the paper found that using an auxiliary loss combined with a simple linear router architecture yielded the best performance. This setup effectively reduced those dead tokens that never get selected by the final recursion, and achieved near-perfect separation of the router outputs. Selected tokens were sharply concentrated near 1.0, unselected near 0.0. Very clear decisions.
Okay, so auxiliary loss was key for expert choice. What about token choice?
For token choice, remember the main challenge is load balancing. They found that using a balancing loss provided stable and accurate routing. It led to a significantly lower max VO, that load imbalance metric, compared to the loss-free methods they tried.
So the balancing loss really helped manage the uneven distribution.
It did, despite the inherent challenges of token choice. It underscores how important a robust routing mechanism is for Moore's efficiency gains, whichever strategy you pick.
And the KV caching strategies. Any surprises there regarding the trade-offs when they looked closer?
Well, one interesting finding was that KV sharing, reusing the first step's cache, worked quite robustly, even in standard parameter shared architectures like recursive transformers. It didn't often hurt performance when models were pre-trained from scratch.
Oh, really? It didn't degrade performance?
Not significantly, and sometimes it even acted as a kind of regularization technique, slightly improving vanilla models.
Why would that be?
The paper provides some evidence suggesting why. They showed that shared layers tend to exhibit highly consistent magnitude patterns and high cosine similarity in their KV pairs across recursion steps. This supports the idea that these KV pairs can be effectively shared without losing too much crucial information.
Okay, that makes sense. But how did KV sharing interact with Moore specifically?
That's where the trade-off appeared again. KV sharing slightly degraded performance in expert choice Moore. This suggests that the benefits from block local computation for attention might be more important when using expert choice routing.
I see.
But conversely, KV sharing actually benefited token choice routing. The thinking there is that the additional contextual information from the shared KV pairs might help compensate for the potentially weaker or less granular routing decisions made by token choice.
So again, it's a trade-off depending on your routing strategy and what you prioritize, local compute or shared context.
Exactly. It depends on the setup.
That's an interesting detail. What about how Moore scales? Does it follow the same scaling laws we've seen discussed for other large models, like the chinchilla laws?
Not entirely, no. The compute optimal scaling analysis yielded a really interesting finding. Moore seems to exhibit a distinct compute optimal scaling behavior. It has a larger slope in its optimal path.
A larger slope? What does that mean practically?
It means that Moore benefits more significantly from increasing the parameter count using larger models than from simply increasing the training data length under the same total FLOP's budget.
So for a given amount of compute, it's better to invest in a bigger Moore model rather than just feeding a smaller one more data.
That's what the findings suggest, yes. It appears to be less data hungry than the baselines. The optimal scaling policy for Moore models seems to favor allocating resources towards increasing model capacity rather than just more and more data.
So the model needs to get smarter internally, capacity-wise, rather than just seeing more examples. That's a subtle but important distinction.
It is.
Did they also look at what the router was actually doing? Like how it was deciding which tokens needed more processing? Was it making sensible choices?
They did, and it's quite insightful. The routing analysis provided qualitative evidence showing that the allocation of recursion depth reflects token semantic importance.
Meaning?
Examples from the paper show the More router allocating more recursion steps to content-rich tokens, like nouns and key verbs, people, drugs, things like that, while function words, like and, the, or punctuation like dashes, tend to traverse fewer steps.
Ah, so it's spending more compute on the words that carry more meaning.
Precisely. The pattern indicates that recursion depth directly aligns with the semantic importance of each token. It allows the model to focus its computational thinking where it matters most. And quantitatively, remember, the expert choice router with auxiliary loss achieved that almost perfect separation in its output scores, near 1.0 for selected, near 0.0 for unselected, indicating a clear, decisive routing mechanism at work.
That's a great example of the model being intelligently adaptive. And finally, what about test time scaling? Can you adjust the compute during inference after the model is trained?
Yes, and this is another powerful capability of more test time scaling. You can allow deeper recursion during inference than what was used during training.
How does that help?
Well, increasing the number of recursions at test time, say, from 2 to 3 or 3 to 4, consistently led to cumulative log likelihood improvement in their experiments. This suggests that each subsequent recursion step can further refine the token representations. So allocating more recursion steps at inference time can indeed improve generation quality.
So you have a flexible knob to trade off quality and compute during deployment.
Exactly. More flexibility in inference time. Now, just to contextualize more a bit, within the broader landscape of efficient transformer research, it clearly builds upon existing ideas in several ways.
Right.
It extends earlier recursive transformers, like the universal transformer, by introducing that variable recursion depth per token. That's key. For adaptive computation, it connects to early esseting methods and, maybe more directly, to mixture of depths, applying MOD's kind of routing mechanism to recursive transformers. That enables arbitrarily deep adaptive compute. When it comes to the routing mechanisms themselves, Moore clearly draws on established concepts from mixture of experts frameworks, particularly token choice and expert choice routing ideas. And for key-value caching, Moore relates to prior work on reducing KV cache size, things like quantization, discarding less important entries, or sharing across layers. Moore offers a complementary approach by reusing KV caches generated in early recursions and later ones.
So it fits into several ongoing research streams.
Definitely. And maybe most fundamentally, Moore inherently enables a form of latent reasoning by adaptively determining the thinking depth for individual tokens, moving beyond those fixed depth approaches we talked about earlier.
So wrapping up the core findings, Mixture-of-Recursions presents this unified transformer architecture. It simultaneously leverages parameter sharing, adaptive recursion depth, and efficient KV caching. And it does all this while maintaining or even improving model quality and throughput. It really does feel like a significant step forward.
It absolutely is, which naturally raises the question, what are the next crucial steps for Moore? The paper itself identifies several key limitations and important future directions.
Okay, what are they?
Well, one critical area is exploring reasoning Moore models. This involves investigating how the router can dynamically learn to adjust to the necessity of, say, chain-of-thought reasoning chains when Moore models are post-trained on reasoning datasets.
Ah, so can it learn to think deeper specifically for reasoning tasks?
That's the hope. It could potentially enhance reasoning accuracy, but also improve computational efficiency and maybe even interpretability, seeing which tokens trigger deeper recursion during reasoning. Another obvious direction is further scaling model family. The experiments reported went up to 1.7 billion parameters. Scaling more models further, maybe over 3 billion parameters, and training on larger corpora is a natural next step, perhaps through continued pre-training from existing large LLM checkpoints.
Makes sense. Keep pushing the scale.
Then there's adaptive capacity control. This is a challenge, especially with expert choice routing. It's hard to adjust those top K values after training, so developing more adaptive model designs that can leverage different capacities during both training and inference is needed.
More flexibility after training.
Exactly. Furthermore, compatibility with sparse algorithms looks promising. Integrating structured sparsity techniques like pruning or quantization with Moore's token-level adaptive recursion could lead to even greater efficiency improvements, combining different efficiency methods.
Stacking the benefits.
Right. And finally, the expansion to multimodal and non-text domains is highly relevant. Moore's recursion block is fundamentally modality agnostic. This means its adaptive depth mechanism could potentially be extended to vision, speech, and unified multimodal transformer architectures.
So applying the same think deeper when needed idea to images or audio.
Potentially, yes, offering significant memory efficiencies and throughput gains, especially for processing long context streams in any modality.
So what does this all mean for you, our listener, an expert in machine learning, data science, mathematics? You now have this comprehensive understanding of Moore, but consider this provocative thought stemming directly from the research. If Moore's adaptive recursion allows a model to think deeper only when truly needed, how might this fundamentally change the way we design and evaluate models for complex reasoning tasks in the future? Are we moving beyond fixed computational budgets towards truly dynamic, intelligent allocation of thought? It's a shift from pure brute force to, perhaps, intelligent nuance. We encourage you to consider these questions and explore the cited research yourself if you wish to dive even deeper into this fascinating and potentially transformative area of efficient model design.